Hello, hello, it's Brian from Tavarin Games here with episode 6 of our strategy map generating tutorial. This tutorial series is starting to get a little bit long, but we just have so much to cover. So in this one I want to cover developing continents and islands. So in our current version of the tutorial of the map maker, the land masses appear just completely randomly and you don't really have any control over where they're going to be and their shape. However, I've coded into my larger version a way to corral them, to change how they are. So you can do a Pangea, where you have a sort of ocean separating one large landmass. Continents, where you can generate, in this case, I go for two sort of larger continents. We can generate another, so you can see where you basically get two continents separated by ocean. And then large islands and small islands, where you have this more clustering into different island sizes. So in order to do that, what we have to do is we have to separate where the land masses are generating and then surround them by ocean a little bit. So when we look at our map, so let's go find it. There it is. We want to break up this map into squares where we can place the islands with ocean boundaries around them. So let's say we want to do two major clusters, so that would sort of generate two large continents. We want to basically just split the map in half, add an ocean boundary within that half for it, and then only place islands within the boxes inside that boundary. And that way we'll end up generating sort of a landmass over here and a landmass over here. If we want larger islands, we want to draw in, maybe 8 boxes, so like 4 by 4 on each. Do their boundaries and add them in. And then for small islands, we want to box them in lots of little tiny boxes and only start them from there and start smaller land masses to keep them from growing into each other too much. Okay, so how are we going to do that? Well, let's go to our strategy map tutorial code and get the strategy map open. We're going to do this entirely in the map maker. We're going to have to scroll up in this case into the generate2 function. Again, we split that off from generate1 so we move the camera first. And after we've drawn the hex tiles, we need to then calculate how many boxes we want and how we want to separate that. So we're going to need a new public integer. So we're going to do this after the frequency. We'll call this public int, and we're going to call this cluster. And then we're going to set this equal to 1 for now, which means, and what this integer is going to be, is how many land masses, so of these masses, how many we want per segment. Okay? So if we want to set it up so that we only have 2 sections, so we generate 2 large continents, if we have, say, 15 land masses, we want half that in each, so 7.5, and then we'd round that up to 8 in each. If we want 4 sections, we would divide this by 4, so it would be 4 land masses per section, and then we'd multiply that, or round that up, so we'd end up with 16 masses total. So, and if we set it to cluster 1, that means we want 1 mass per segment, so we're going to have 15 separate segments, or close to it. So the first thing we want to do is we want to calculate the ratio of the map. So we're literally going to call that ratio, and this is going to be the map size.y divided by the map size.x. So that is our height to width ratio. And actually, okay, we don't have to declare float because they already are. Good. So then what we're going to do, we're going to want an integer. We're going to call it y units. This is going to be the number of vertical boxes we try to create. And we're going to set that to 1 to start. We then want to calculate our masses, or basically the number of boxes we want. I'm just going to call that mass. And that's going to be that rounding up. So mathf.ceil to integer. And then that's going to be a float of the masses. We got to do that right. And then divide that by the cluster value. Okay? So that's the number of boxes we're going to need. And then we can calculate our x, or make our x units. So that's the horizontal number of squares we're going to try to create that we're going to fill, and equal to the mass that we just calculated. And then what we want to do is we want to calculate the old difference, or what we're going to call the old difference. And that's going to be a new vector 2, and then that's going to be a float of the y units. divided by the x units, and then the y units. So this is our previous attempt. The reason we're calculating this is what we're going to do is we're going to go through a while loop, and we're going to try to calculate out the best series of rectangles or that are closest to squares to fill the space. So let's say our map is 2 times as wide as it is tall, and we need to fill it with 8 boxes. Well, if you have 4 by 2 boxes, then they're perfect squares, and that's what we'd want. Right now, though, we're starting with 1 by 8. 1 by 8 is not great. We don't want to do that. So we want to then look at, okay, if we make y equal to 2, how many x units across get us close to that? How close is that to the number of masses we intend, and how close is it to the ratio? And we need to take the old version of that, so right now the initial solution, so we can compare that to our new solution. So we need a Boolean. We're going to set that to false. As usual, we're also going to track attempts. Now, we're already tracking attempts down here, so we can actually get rid of this integer declaration because we're going to redeclare it up here, equal to 0. And now let's set up our while loop that's going to try to find the optimal set of rectangles to fill in our space so that they're the closest to squares as they can be, and close in number to the number of boxes we want. All right. That may have sounded a little confusing, but let's just jump into it, and hopefully you'll see how we're doing that. So we always rack up our attempts when we first start a while loop. So what we do first is we add 1 to the y units, and then what we do is we make the x units equal to mathf.ceil. We're going to round up to integer, and we're going to do the mass divided by the y units, and again, always as a float, just so that we end up with y units. We want to declare as a float so that this doesn't pre-round to an integer and screw up our ceiling method here. Okay, so we have our new x units. We're going to have a new ratio. So we'll call this new ratio, and that's going to be, again, float of the y units divided by the x units. Okay, so we have our new ratio, and we can compare that to the desired ratio, and we're also going to compare the old ratio to it. So we have an if statement. So we want the mathf dot absolute, so we want to subtract that ratio minus new ratio, and we want to see if that is less than or equal to our mathf dot absolute. Again, we want to round this because the new ratio can go lower than the old one if we want. Ratio, and then minus the old difference dot x, because we already calculated a ratio here. So what this is doing is it's calculating the ratio and tracking the old y units, and then we storing that so we can use it in the future if the new ratio is not great. So if that's true, or if our new ratio is less than or equal to our old one, we want to just move forward with the new one. So we set the old difference equal to that ratio, new vector 2, and then this is going to be the same, basically the new ratio, because we have already calculated it here, and then the y units there, and then else. Otherwise, though, we have found our best. The previous ratio was better, and we want to keep that. So we just lock that in. So y units is equal to the integer of old difference dot y. We don't need the ratio. We just need that for calculations. So x units is equal to this. We're going to recalculate. Dot ceil to int our mass divided by our float y units, which is the same as before. Now you could store the x units, y units as a single vector too. I like to declare them separately just for clarity in my mind. And then we have a solution. So we're going to set solution equal to true, and that'll break the while loop, and we are good to go. Okay, so we have our box of clusters left and right. So now we need to calculate how big they are. So let's do, we're going to do x base is going to be the size of them. So the base size of it in the x direction, and that's going to be mathf dot round to int. In this case, we're rounding it, so the map, we don't need to actually do this as float because the map size dot x is already a float, divided by x units, and then the integer y base, and again, these have to be integers because we're dealing with a discrete number of tiles at all times. So we're going to round int the map size dot y, and then divide that by the y units. Okay, so that's how big the boxes are that will fill up our total map size approximately. It doesn't need to be exact. With the way we calculate it, it just means maybe at the edge of the map, the boxes where it can possibly start something are slightly smaller. But that's fine. And now we're going to do variables I call x limit is going to be the border, the water border we want to keep the islands from getting too close. Otherwise, it'll just end up looking random or close to random. So in this case, we want to floor it. And we're going to take the x base and we're going to divide by 5f. So only the so 20% on either side within the x base will have to be water, and we can only start a landmass inside the internal 60%. And we're going to do the same in the y, so we can just copy that, y limit. So x base, instead of x base, y base here. Okay, so we have our total map thing. Now, the other thing we want to do is if we are clustering into the masses, so if clustering is equal to mass size, so that means all of the masses end up in one cluster. So if cluster is equal to masses, we don't want them to be quite so far apart. I've found that there's just no room for them to go. So we're going to have the x limit. In this case, oh, that needs to be an equal sign. So we have the x limit in that case, again, because in this case, we're putting all the masses into one Pangea-sized thing. And if we keep x limit as 20% on either side, 40% of the map is going to be ocean. And you end up with this massive ocean in the sort of on the side of the map. And it ends up being really far away from the other side. And I found that that just doesn't look as good. So we want about half that. So we still have that ocean between it, but the ocean's not so massively big. Okay, so we track our mass temps, masses. So now we need to actually calculate where the masses are going to go. So we have our while loop from before, where we take a temporary integer of the number of masses we want, we go through and we place them, and in this case, it's just randomly anywhere on the map. So what we actually want to do is we want to do this for each of our boxes. We have our ratio x units and y units, so we want to go through those boxes, and we want to place the number of masses into each of those that we're supposed to, our cluster amount. So we're going to nest this inside a pair of for loops. So enter x is equal to 0, x is less than x units, and then we're going to go up x plus plus. So we're going to come down to the end of the while loop, because the while loop, we want to stay pretty much the same. But we want to encapsulate that. Now, the first thing we need to do is calculate where our x can go. So I'm going to do a new vector 2. And I was running out of names at this point. I just called it x limits with an s. And this is going to be a vector 2 that declares where the box boundaries are. So this is where we're going to calculate. So it's x times x base is our low end plus the x limit. So that is our water barrier on the left. And then x base minus 2 times x limit. So this guarantees, in the case where we have really small boxes and x limit rounds to 0, this guarantees that we have some water boundary. So what we're doing is this is our left-hand side, and then this is how much further to the right it can go. Okay, so we calculate our x limits for that. We then need a y loop, our loop for the y. So y equal to 0, y less than y units, and then y plus plus. We're going to encapsulate the while. Once again, the entire while loop is going to go into that. So we're going to go through all of our x units and then all of the y units we need within that, and then we're going to run our while loop. So we also need our y limits vector 2, and that's going to be calculated the same way as our x limits. So we copy this, bring this down, make this y limits, y times y base plus y limit, and then y base minus 2 times y limit. Okay, so we have this, we have our limits, we are bringing them in, and now we have our masses. The mass temp we need is going to equal that cluster amount we set. So that's, as I said, that's the number of masses we're trying to place in each of these boxes, so that's what that is here. So you're going to sometimes end up with more than your total number of masses. If this calculates out, as I said before, like let's say the map is 4 by 2, or maybe it's 1 by 1, like it's 1 ratio, and we're trying to put 14 boxes into it, this will calculate that the best solution actually has 16 boxes because it wants 4 by 4. But it will make sure that we always end up with a number of boxes that fills the screen, and each of those boxes is as close to a square as can be. So the last thing we have to do is, of course, restrict our position that we're going to calculate for our clusters. So we need to go here. So we need the new position. We still want to round it as the x limits dot x. So that's our low point we can be. And then we're going to add to it a random dot value times x limits dot y. So what that's going to give us is a value between the low point we calculate and then up to that sort of 60% higher in the box. So that's why we did the 2 times x limit here. And then for the y, we want to do the same thing. So it's y limits dot x plus random dot value times y limits dot y. So again, we are calculating from the x point over to the amount above that we've calculated to keep the masses within the center 60%. So we have our new position. So let's go into our tutorial and see what that did. So over here, we've got 30 masses and clustering is set to 15, so half of that. So let's press play and see what it does. So zoom out and look at that. We have 2 separate continents because, again, our clustering is half of the 30. If we set this to 1, it should be basically randomly distributed. Now, because the islands are quite big and the map is small is why we're getting that. So let's make our map a little bit bigger so we can see it better. And there we go. You can see we have islands evenly distributed. Again, they're bigger islands, so let's make them really small so we can see this. And there we go. You can see we have completely evenly spread out islands, still with some randomization of the placement. And then you can tweak the sizes to try and get something where you've got, yeah, like small islands like an archipelago with a lot of ocean between. But again, we want to set the clustering. Let's say we want 4 boxes. So 30 divided by 4 is about 8. We're going to have a little more. And look at that. So we basically get 4 separate continents horizontally. If we make the masses a little bit bigger, maybe they'll grow into each other. Yeah, so that's when they start growing into each other. They're a little too big. So you'd have to tweak the settings for the different map modes you want. And then if you want a Pangea map, we put it all into one box, and they should all clump together in one. Now, we don't have enough land to fully fill that, so we can make this bigger. Let's try 8 to 9. And there we go. Yeah, we end up with one Pangea continent because it's all clustered together, and then a nice little ocean between. But it's not too far apart. As we talked about, if I didn't limit that in the code, actually we can do that right now. If we get rid of this chunk of code here where we are dividing the cluster, let's save that and recompile it. It should make the ocean really big. Let's take a look at that so you can see why I've done that. Oh, actually, yeah, in this case, there's where that center ocean is. For some reason, clustering set to 15 still. Set clustering equal to the number of land masses and generate. And you can see that we have a really wide ocean here. So that's why that line of code is in there. You don't need it. You can leave that out if you do want a really big ocean on Pangea style maps. But I don't. I want the ocean between to be a little bit smaller when we're doing that type of continent. So again, we'll go back to Pangea style, and we end up with a smaller ocean and then one landmass. In this case, a lot of lakes because we haven't really filled the landmass in, so maybe we start with 45 masses to really fill it in. We got to set this to 45 as well. So if you want a Pangea, your clustering value has to match your masses. And yeah, we end up with one nice Pangea and then some lakes and all that. So there you go. That is how we can control our island generation so that it fills the map up in the way you want. So again, if it's half the clustering, you end up with 2 zones, 2 separate continents. If it's 1/3, you should end up with 4 separate continents. So you can always play around with this as you want, but this will let you have a lot of control in sort of the island shapes and where they go. They do start to grow into each other if you have them a little too close. And you can tweak your X limits to change that, to have more ocean and really restrict where the island starters can be. Or you can go fully random, so you get full random distribution if you set the clustering to, or not quite full random, if you set the clustering to 1, fully evenly distributed around the map. So that's all I have for you in this tutorial. If you made it this far, thank you for watching. Again, as always, please let me know if you have any suggestions on how this could be improved or done differently. And as always, have a good one.